Hello, I'm Anirudha, first year master's student at University of Montreal. I'll be presenting today our work on AI-based modeling of brain and behavior, combining neuroimaging, reinforcement learning, and video games. Video games provide a promising framework to link brain activity and behavior in a naturalistic and complex setting. We record brain and detailed behavioral data while subjects play Shinobi 3 video game inside a scanner. We hypothesize that brain activity measured using multimodal neuroimaging could improve the way we train ANNs and at the same time help us understand biological cognition. For further details on motivation behind using video games, do check out our March 19 talk by my colleagues Andre, Jan, and Bessie. In this talk, I will start by briefly introducing the game. Then I'll present how a reinforcement learning model taught me new ways to play the game. Following that, I'll present one of the milestones in our project, achieving near perfect imitation of subjects' gameplay. In the end, I'll be discussing our works relating to discriminating between players given their gameplay and techniques developed to understand the feature space of our deep learning models. Let's start by understanding the basics of Shinobi. This is how a Shinobi 3 game looks like. So this is the Shinobi. It can move right, it can move left, it can jump, it can sit, throw shurikens, jump, throw shurikens, and all combinations of actions are possible. And it can run, and there are enemies which it must kill. So you can set shuriken. There are bigger monsters, pick up weapons, kill, and yeah. So this is the flavor of the game. It can jump and shoot, and it can move right. There's also a sword which some subjects use. You can jump and kick, and yeah, this is how the gameplay looks like. We wanted to first look into the kind of models that would be required to play this game. In the reinforcement learning setting, there are two main components, an agent and an environment as shown in the figure. The agent acts on the environment and the environment provides the next state and the reward. Video games are classic examples of problems in such setting. Deep learning revolution in the past few years have enabled us to solve the reinforcement learning problems. We adapted these four following algorithms to our game. DQN and recurrent version of deep recurrent Q-learning were not able to solve the problem due to the richness of the game. Actor-critic models, A3C, in principle worked, however failed due to compute issues. Hence, the GPU version of A3C model was finally able to solve the game. In deep reinforcement learning setting, the algorithm learns by itself what actions it must take by interacting with the game multiple times. Hence, the strategy it comes up with is not hand-coded. Let's now look at how a model that learned to play the game by itself look like. We saw that a deep learning model can learn to play the game by itself. However, it came up with a strategy that might be different from our subject's gameplay. We wanted to come up with an AI model that can play like the subject and further use it to compare its activations to the brain activations of the subject. For this imitation learning problem, we use behavioral cloning approach where we treat it as a supervised learning problem. Alvin paper published in 1988 is one of the first works to train a self-driving car based on this behavioral cloning, where they train it to drive itself using the expert's data. Here, given the input game state, we want our model to output actions similar to what subject would take in that situation. We tried three deep learning architectures to solve this problem. At first, we tried a normal CNN model which failed due to the temporal nature of the game. Hence, we further tried CNN model with an LSTM layer, which failed when trained normally. Further, we trained the CNN LSTM model with a weighted loss function where we were able to achieve nearly perfect imitation of subject's gameplay. The architecture from our final model is shown here. From the bottom, an RGB frame of the game is passed to the CNN layers that process visual features, and the output from them is passed to the LSTM memory layer that helps in maintaining the temporal state of the game. Further, it is passed to the fully connected layers before outputting the actions. So, why was weighted loss crucial to achieve imitation? There is huge imbalance in the action sequences. As write is one of the most frequent step in the sequence, an example sequence would look like 2220 where 2 is the action number for move right. This is a major problem in training neural network as the data must be balanced. This cannot be resolved as we resolve in normal supervised learning problems by removing some percent of twos from the data, as it's a sequence and without even one two, the action would be different. Hence, we use a weighted loss function where the weight is based on the frequency of each action in the data. So if while training, if it makes error on frequent actions, the penalty is lesser than if it makes mistake on infrequent actions. This allows the model to focus more on the infrequent actions as well. Let's look at how it imitates our subject's gameplay.
First, let me consider my own gameplay, um, and let's see how the gameplay works. Here, you'll mainly I observe that whenever the enemy is present on the tree, I jump and shoot, and whenever there is a normal enemy on the ground, I sit down and throw arrows at the enemy. This is my signature move, normal walk. Then whenever enemy is there, sit and shoot, sit and shoot. So when we see how an imitation learning network trained on my gameplay does, we observe that it walks, sit and shoots, jump and throws, sit and shoot, sit and shoot, and then when nothing is there, walk, jump, shoot, and again sit, shoot, and the strategy, you will see that it's quite similar to what I employ. Now let's compare subjects one and another subject strategy, which is more complicated. Here, the subject runs, slashes, or jumps and kicks. So here he jumps, kicks, and then jumps, kicks, and you might notice that he doesn't bother about the enemy sitting on the tree. Here jump, kicks, and jump, kick, and again run, jump kick, or he might use his sword, which is again uncommon in the previous subject strategy. Here jump, kick, and move forward. Now coming to what the imitation learning model learning learns, you see that it also runs, and run and slash, jump and kick, exactly as the type seen in the real player. One thing we must notice is that this sequence of actions of running and slashing or jumping and kicking is like very hard and possible only for expert players, because it requires precise timing of jump. And I think this is why we said that we required a weighted loss function for it to be able to catch those minute intervals, when minute actions which are very rare but very significant, while the most frequent is moving right, which is the most frequent action. Now we see again that it jump kicks, again use the sword. It also does mistake few times because it's not infallible, but most of the times you see that it gets the kicks almost at perfect times. So this was only for a part of a level which I showed, but we see that similar, we get approximately same behavioral strategies on both the players on the entire levels.
Further, we wanted to see how well a classifier could discriminate between subjects' gameplay. Now we have the following attributes from the raw user data: actions, which are scalars; observations, which are in the form of RGB game images. The gameplay of the subjects is temporal in nature. We used sequence of 20 time steps to classify which subjects it belongs to. On looking at two subject classification, these were the following results. Assumed decision trees, fully connected neural network, and fully connected neural network with LSTM, all classified with the help of only actions. We use CNN with LSTM for classifying from images. As expected, images contain more information than just action, and hence the CNN LSTM network was able to perform the best. Shown here is the CNN LSTM model that was used to discriminate between the subjects given their gameplay as inputs. It's similar to the architecture for imitation learning, but now it is, instead of predicting actions at each time step, like in case of imitation, here at the end of 20 time step, the network outputs which subject it came from. We wanted to develop a framework to understand the feature space of all our CNN LSTM models. In this work, I have used discriminated network as example, but the same method can be applied to the imitation learning network or to the RL model, which relies on CNN LSTM type models. We used outputs of LSTM layers to understand the network, as these contain spatial as well as temporal information encoded by the model. The feature vector size is of 2000. There are like 20 time steps, and each time step there is a vector, hidden size vector of 100. For labeling the points, we have the following three attributes. There is a subject label to see which subject it came from. There is a time point of the sequence in the game, and in order to understand what is actually happening in the sequence, we concatenated 4 observations from the sequence of 20 observations. The above information is explained in detail in the next slides. As we can't visualize a 2000 dimension vector, we tried 3-dimensionality reduction algorithms. Principal component analysis that finds the principal components along which the data variance is maximum and projects the points along those components. T-SNE, one of the most popular techniques to visualize high-dimensional data, and UMAP, which preserves more of a global structure in the data and is more speed efficient than T-SNE. While 2D scatter plots are informative, it's hard to look at what each of these points represent, especially if each point is a sequence of 20 frames. Hence, we adapted the Tensorflow embedding projector to our custom data. This projector enables us to run various clustering algorithms on the fly in our browser and also change various hyperparameters of these clustering algorithms. And look how it affects these projections. Let's look at how the projections look like.
There in the lower left bar, there are like three things, right? Like UMAP, PCE, PCA, and three things which customizes on the fly, as we'll see shortly. And the colors like are labeled like from maybe you can rotate a bit. Yeah, are our gradient based colors, and dark blue indicates like 55. Like we had said that the labels are like the position labels are labeled from 0 to 1 based on which part of the run it is in. So the dark blue indicates that it's in a more deeper run and things like that. And this is the projected screen. Now let's run TSME over there. Yeah, so you see that this is the initial embedding, and this is like as the TSME iterations proceed, the data sets are splitting. Now, I think you'll find that it is mainly splitting into two clusters now. I think, Yeah, I think it's almost done with two clusters. You can stop the thing. And now we can see that let's suppose go to one particular part of the embedding, right? So we can just select that. There is a select button. No, max that top left one is no, no, top left. Yeah, you can select a little bit. Yeah, 10 or 20 points like that. Yeah, now we see that you can isolate that particular region itself, isolate just 21 point. Now we can see that everything in the search page in the right column arranges from like 47 to 53. So we see that in the later parts of the game, in the ending parts of the game, the sequence actions and the features are similar to each other. So that's why you find like all this, you find that cluster too. So this is one cluster. Now when we zoom in on it, now this is the point which I was talking. I concatenate frames. Now each frame, you can zoom in a bit more. Maybe is it possible? Oh no, it's fine. So here you see that it's concatenated with like 4 frames, and all are like there is a cave and there is monster and how it attacks. So that is the sequence capture. Now when you see some other frame in this cluster, you see again it's the monster and the cave part itself. Now we find that all other clusters are cave and monsters, and all are see sequenced and similar to each other. So we can also find, you can again do show all data points. So this was that particular cluster, and now we also have we can visualize. This is only PCA. Now let's try UMAC now. So run. Can you do run? Right? So you see that UMAP is also running on the fly, and you see UMAP is, since it takes more of a global, this one here split into more two clusters, much more than anti-SNE due to this being a discriminant network with two different subject actions. So all this are clustered here, and all the other subject actions are clustered in the second cluster. And you can again, there are internal clusters also which you can zoom in and see. And yeah, so I think this should be quite helpful to visualize the decision of LSTMs and have some fun.
To conclude, here I have presented the initial work of my master's project and believe this would serve as the basis for the next steps. We started off by understanding the game environment and modeled it using deep reinforcement learning techniques. Then perfect behavioral imitation of subject's gameplay was achieved, which we'll further use it to compare with the brain data of the subject. We discussed about the classification of subject's gameplay and also set up a framework for visualization of feature space of our CNN LSTM models. Currently, we are working on prediction of brain voxel values from the imitation learning network activation values using regression. And by the end of this term, we plan to explore classification of strategies on all 6 subjects, visualization of latent space on imitation learning network, and further, and by similarity analysis of imitation learning activations, hand-crafted features, and the subject's brain data. In the following academic year, we intend to perform similar analysis using MEG video game data and further explore domain adaptation between fMRI and MEG data. I would like to thank my supervisors, Dr. Karim Jobi and Dr. Pierre Belek, the entire NeuroMod project team, and Courtois Foundation for giving me the opportunity to work on this amazing project. Thank you.